The Alpha Centauri system is a fascinating and complex star system located in the southern sky, approximately 4.37 light-years away from Earth. It consists of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, and it is the closest star system to our own solar system. The Alpha Centauri system has long captured the imagination of scientists and science fiction writers alike, and it has been the focus of numerous studies and missions designed to better understand its structure and properties. With the potential for habitable planets and the possibility of interstellar travel, the Alpha Centauri system holds remarkable promise for the future of space exploration and for deepening our understanding of the universe. Subscribe and explore every aspect of this journey as we uncover many mind-blowing facts about interstellar travel. Sights of Proxima Centauri. What do we expect to see if we travel to Proxima Centauri? If humans were to journey to Proxima Centauri, the closest star system to our own, there would be several extraordinary sights waiting to be revealed. First, Proxima Centauri is a red dwarf star, meaning it has a much lower mass and luminosity than our Sun. As a result, it would appear far dimmer and noticeably redder in the sky compared to the bright white light of our Sun. In addition, Proxima Centauri hosts 2 known exoplanets within its habitable zone: Proxima Centauri B and Proxima Centauri C. Proxima Centauri B is the closer of the 2 worlds and is believed to be a rocky, Earth-like planet with a mass comparable to Earth. However, because it orbits extremely close to its star, it is most likely tidally locked, with one side permanently facing the star in constant daylight, while the other side remains trapped in endless darkness. If humans were ever able to land on Proxima Centauri B, they would encounter an environment dramatically different from anything on Earth. The star itself would look smaller and dimmer in the sky, and conditions across the planet would be extreme. The day side could reach temperatures hot enough to melt lead, while the night side would remain intensely cold, creating a world divided between fire and ice. Yet with advanced technology and sufficient resources, it is possible that humans could one day establish a permanent presence on Proxima Centauri B, exploring its unique environment and studying its geology, atmosphere, and potential for life. Another breathtaking sight during such a journey would be the Alpha Centauri system itself. Alpha Centauri is a triple star system made up of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B form a binary pair, orbiting a shared center of mass, while Proxima Centauri moves around them at a much greater distance. From close range, these 2 stars would appear to circle each other in a slow and graceful cosmic dance. Observers might also witness the powerful gravitational interactions between the stars and any nearby planets, revealing the dynamic structure of this system. Preparing for the journey. Before embarking on a mission to Alpha Centauri, scientists and engineers would need to design a spacecraft capable of surviving the extreme conditions of interstellar travel. This spacecraft would need to be equipped with everything required to keep astronauts alive and healthy for the entire duration of the journey, which could last decades or even centuries. One of the greatest challenges of interstellar travel is the sheer distance involved, at a distance of 4.37 light-years. Even a spacecraft traveling at the speed of light would still need more than 4 years to reach Alpha Centauri. However, current technology is nowhere close to achieving such speeds, which means alternative propulsion systems must be considered. One of the most promising options is nuclear propulsion, a method that uses the energy released from nuclear reactions to generate thrust. This technology has the potential to dramatically increase both the speed and efficiency of spacecraft, making it an attractive solution for long-distance space travel. The core concept behind nuclear propulsion is to use a nuclear reactor to heat a propellant, such as hydrogen or helium, to extremely high temperatures. The resulting hot gas is then expelled through a nozzle to produce thrust, in a way similar to a traditional chemical rocket. However, because nuclear reactions release far more energy than chemical reactions, nuclear propulsion systems can generate significantly greater thrust. Over the years, several different types of nuclear propulsion systems have been proposed and developed. One of the earliest concepts is the nuclear thermal rocket, which relies on a nuclear reactor to heat hydrogen or another propellant before expelling it to create thrust. This technology was developed and tested by NASA during the 1960s and 1970s, although it has not yet been used in an operational space mission. Another approach is nuclear electric propulsion, which uses a nuclear reactor to produce electricity that powers an electric engine. While this method is far more efficient than chemical propulsion, it generates lower thrust, making it better suited for long-duration missions rather than short, high-speed travel. Despite its potential, nuclear propulsion also comes with significant challenges. One of the most serious concerns is safety, as nuclear reactions can produce harmful radiation and carry the risk of catastrophic failure. In addition, engineers must overcome the difficulty of designing and building a nuclear reactor that is both compact and lightweight enough to function effectively in the harsh environment of space. Overall, nuclear propulsion is a highly promising technology that could transform space travel in the years ahead. With continued research and development, it could enable faster and more efficient missions to destinations like Mars, the outer planets, and even regions beyond our solar system. Nuclear-powered rockets could potentially reach speeds of up to 10% of the speed of light, which would dramatically reduce the travel time to Alpha Centauri. However, this technology is still in its early stages and is not yet practical for interstellar missions. Another approach is the use of solar sails. Solar sails are a type of spacecraft propulsion system that relies on the pressure of sunlight to generate thrust. Unlike traditional rockets that depend on chemical reactions, solar sails use the momentum carried by photons from the sun to push a spacecraft forward. The basic design of a solar sail includes a large reflective surface made from extremely thin and lightweight materials such as mylar or captain. When sunlight strikes the sail, photons bounce off its surface and transfer a small amount of momentum. Over time, this continuous pressure can gradually accelerate a spacecraft to very high speeds. Solar sails offer several advantages compared to traditional propulsion systems. They do not require fuel, allowing them to accelerate continuously as long as they remain exposed to sunlight. They are also capable of reaching much higher speeds than chemical rockets, making them well suited for long-distance space travel. In addition, their relatively simple design and lower cost make them an attractive option for future missions. Despite these advantages, solar sails also face important challenges. Sunlight provides only a very weak force, which means the sails must be extremely large to generate meaningful thrust. Their effectiveness also depends on their orientation, as they must be positioned correctly relative to the sun, which limits their flexibility for certain mission profiles. Even with these challenges, solar sails have already been successfully tested in space by several organizations, including NASA and the Japanese space agency, JAXA. In 2019, the Planetary Society launched a small spacecraft known as LightSail 2, which demonstrated the practicality of solar sailing in space. With further advances, solar sails could become a key technology for exploring the solar system and beyond. Regardless of the propulsion method used, any spacecraft designed for a journey to Alpha Centauri would need to withstand the extreme conditions of space, including radiation, micrometeoroids, and severe temperature variations. It would also need to carry everything required to support human life for the entire journey, including food, water, air, and systems to manage waste. This raises a critical question. Would any amount of food or water truly be enough to survive such a journey? The answer depends on both the duration of the mission and the number of crew members aboard the spacecraft. Since current technology cannot achieve interstellar travel within any reasonable time frame, the journey would likely take tens of thousands of years, making it impossible to carry enough food and water to sustain human life for the entire trip. If we assume a single generation lasts around 25 years, then over a span of 10,000 years, there would be roughly 400 generations. This is only a rough estimate, as the length of a generation can vary depending on culture, lifespan, and social structure, but it gives a clear sense of the immense timescales involved in interstellar travel, and the reality that such a mission would have to be completed by countless generations of humans. And when you really think about it, the idea sounds almost unimaginable. Imagine entire families living and evolving in space, generation after generation, never knowing the world their ancestors left behind. Instead of attempting to carry all necessary resources, a more realistic solution would be to develop closed-loop life support systems capable of recycling and reusing essential materials such as water, oxygen, and other elements required for survival. Creating such systems would demand extensive research and engineering to ensure they remain efficient, reliable, and sustainable over extremely long periods of time. In addition, the crew would need to depend on advanced food production technologies capable of generating nutrient-rich food from raw materials. Early versions of these systems are already being tested on missions closer to Earth, such as those aboard the International Space Station, but they would need to be significantly expanded and adapted for interstellar travel. Launching the spacecraft would be another immense challenge. Once designed and constructed, it would need to be sent into space through an effort that would likely require collaboration between multiple nations and organizations. A powerful launch system would be needed to carry the spacecraft out of Earth's orbit and place it on a path toward interstellar space. After reaching space, the spacecraft would need to be precisely aligned along the correct trajectory to reach Alpha Centauri. This would involve highly accurate calculations and continuous adjustments to ensure that it stays on course. Even a very small deviation could cause the spacecraft to miss its destination entirely and drift endlessly through space. The first step in planning this trajectory is identifying the launch window, a specific period during which the spacecraft can depart using the least amount of energy. This window depends on the relative positions of Earth, Proxima Centauri, and other celestial bodies within the Alpha Centauri system, and it can vary depending on the intended speed and flight path of the mission. Once the launch window is identified, the spacecraft must be launched with extreme precision to ensure it follows the intended trajectory and arrives at Alpha Centauri at exactly the right time. This requires highly accurate calculations of the spacecraft's velocity, acceleration, and position, along with a deep understanding of the gravitational forces acting on it throughout the entire journey. To determine this trajectory, scientists rely on a combination of analytical calculations and advanced computer simulations. These calculations take into account the gravitational influence of the Sun, the planets within our solar system, and the stars and potential planets within the Alpha Centauri system. They also consider the subtle effects of interstellar dust and gas, which can gradually alter the spacecraft's path over vast distances. Beyond theoretical calculations, computer simulations play a critical role in modeling the spacecraft's trajectory and ensuring it remains on course. These simulations incorporate a wide range of variables, including the spacecraft's mass, shape, and propulsion system, as well as the complex gravitational interactions and environmental conditions it will encounter along the way. One of the greatest challenges in planning such a journey is balancing the energy required to reach the destination with the limited fuel and resources available on board. This demands careful optimization of the flight path, minimizing energy consumption while still ensuring the spacecraft reaches Alpha Centauri within the intended timeframe. To achieve this balance, scientists often use a technique known as gravitational slingshotting, where the spacecraft uses the gravity of planets or other celestial bodies to gain speed while conserving fuel. This method was famously used by the Voyager 1 and Voyager 2 missions to explore the outer regions of our solar system. And it has also been proposed as a possible strategy for missions targeting Proxima Centauri. Another critical factor is ensuring that the spacecraft is not pulled off course by the gravitational influence of other objects. This requires detailed modeling of the complex interactions within the Alpha Centauri system, including the effects of its binary stars and the possible presence of additional planets or asteroids. To maintain the correct path throughout the journey, the spacecraft would rely on a range of onboard systems, including course corrections, thruster burns, and reaction wheels. These systems allow continuous adjustments in response to changing conditions, ensuring that the spacecraft remains precisely on track as it approaches Proxima Centauri. The journey itself would be long and demanding, potentially lasting decades or even centuries. During this time, the astronauts would need to remain healthy and focused, constantly monitoring the spacecraft and making necessary adjustments. One of the most profound challenges they would face is the effect known as time dilation. Time dilation occurs when time passes at different rates for observers moving at different speeds, a direct consequence of Einstein's theory of relativity that has been confirmed through numerous experiments. During a journey to Proxima Centauri, which lies approximately 4.24 light-years away from Earth, this effect becomes increasingly significant as the spacecraft approaches relativistic speeds. As the spacecraft nears the speed of light, time on board begins to slow relative to time on Earth, creating a growing difference between the two. To better understand this, imagine a spacecraft traveling at 90% of the speed of light toward Proxima Centauri. From the perspective of observers on Earth, time aboard the spacecraft would pass much more slowly. For instance, if the crew experienced a journey lasting 10 years, only 1 year would have passed on Earth due to the effects of time dilation. This means that if astronauts aboard the spacecraft were to travel to Proxima Centauri and then return at 90% of the speed of light, they would experience a total journey of about 20 years, while only 2 years would have passed on Earth. This effect becomes even more pronounced as the spacecraft moves closer to the speed of light, creating the impression that interstellar travel might be possible when viewed through the lens of time dilation. A similar effect can already be observed much closer to home in GPS satellites. These satellites orbit Earth at high speeds, and because of this motion, time on board passes slightly more slowly compared to time on the surface. As a result, their onboard clocks must be carefully adjusted to account for this difference. Otherwise, the entire GPS system would quickly lose accuracy. To cope with the effects of time dilation on a long journey, a spacecraft would need highly advanced life support systems capable of sustaining astronauts over extended periods. It would also require facilities for physical exercise, entertainment, and psychological support, all essential for maintaining both the physical and mental well-being of the crew during such an extreme mission. Another major challenge of interstellar travel is radiation exposure. Outside the protective shield of Earth's atmosphere, cosmic radiation becomes far more intense and can damage human cells, increasing the risk of cancer and other serious health conditions. Managing radiation exposure is therefore one of the most critical concerns for both astronauts and spacecraft designers. The space environment is filled with multiple sources of radiation, including cosmic rays, solar flares, and galactic cosmic radiation. Each of these can pose significant risks to human health and can also damage sensitive spacecraft systems. Understanding these different types of radiation is essential in order to develop effective protection strategies. Cosmic rays are extremely high-energy particles that originate from outside our solar system. They are primarily made up of protons and atomic nuclei, and their energy can exceed that of particles produced in nuclear reactors. These particles can penetrate deep into spacecraft, potentially damaging electronics such as computers, sensors, and communication systems. They can also interact with human tissue, damaging DNA and increasing the risk of mutations and cancer. Solar flares present another serious threat. These sudden and powerful bursts of radiation from the sun release large numbers of high-energy particles, including protons and electrons. When these particles reach a spacecraft, they can penetrate its structure and expose the crew to dangerous levels of radiation, potentially causing radiation sickness. Solar flares can also disrupt communication and navigation systems, creating additional risks during the mission. Galactic cosmic radiation is even more challenging. Originating from outside the solar system, it consists of high-energy particles such as protons and heavy ions that travel across the galaxy. Unlike radiation near Earth, it is not shielded by our planet's magnetic field, making it a constant presence during interstellar travel. This form of radiation can damage both spacecraft components and human cells, leading to long-term health effects, including an increased risk of cancer. To reduce these risks, spacecraft designers employ several strategies. One approach is to shield the spacecraft using materials capable of absorbing or deflecting radiation, such as lead or polyethylene, helping to lower the levels of exposure inside the spacecraft. Shielding can be effective in reducing radiation levels inside the spacecraft, but it also introduces significant challenges, adding both weight and cost to the mission. Another important strategy is to design spacecraft that are inherently more resistant to radiation. This can involve using radiation-hardened materials for critical components such as electronic systems and power supplies. In addition, spacecraft can be built with redundant systems, allowing them to continue functioning even if certain components fail due to radiation exposure. One of the most effective ways to reduce radiation risk is to limit the duration of the mission itself. The longer the journey, the greater the cumulative exposure, and the higher the likelihood of serious health effects for the crew. By designing missions that are shorter and more efficient, engineers can significantly reduce these risks. Astronauts can also take direct measures to protect themselves, including wearing specialized shielding garments and using medications designed to lower the risk of radiation sickness. They can monitor their exposure levels and move into more heavily shielded areas of the spacecraft during periods of intense radiation. The spacecraft itself would need to operate as a fully self-sufficient system. Since resupply missions would be impossible across such vast distances, it would need to generate its own power, recycle its waste, and continuously produce its own food and water to sustain the crew. During the journey, astronauts would have the opportunity to observe the universe in ways never before possible. They could conduct scientific experiments, gather data, and study distant stars and galaxies in unprecedented detail. Communication with Earth would still be possible, allowing them to send back valuable information and images from deep space. After decades or even centuries of travel, the spacecraft would finally arrive at the Alpha Centauri system. The primary focus would likely be Proxima Centauri, the closest star in the system. The spacecraft would need to carry advanced instruments to study the star and its planets, along with specialized equipment designed for landing. If any of those worlds prove suitable for exploration, the system itself consists of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are similar in many ways to our Sun, while Proxima Centauri is smaller and cooler. Orbiting within its habitable zone is an Earth-sized planet known as Proxima B, a world that could potentially support life. If Proxima B is considered a viable target, the spacecraft would need to deploy a lander capable of safely reaching the planet's surface. Astronauts would then begin the process of exploration, collecting samples and analyzing the environment. The first step in planning such a landing would be to gather as much information as possible about the planet's surface conditions and its surrounding environment. This requires a combination of telescopic observations, remote sensing, and in situ measurements. Scientists must determine the composition and topography of the planet's surface, along with its atmospheric conditions, temperature, and radiation levels. All of this data is essential for designing a landing system capable of safely navigating and reaching the surface. Once enough information has been collected, the next step is to design a spacecraft and landing system that can operate under these conditions. This involves integrating propulsion systems, guidance systems, and advanced landing technologies. The spacecraft must be able to handle the complex gravitational forces within the Alpha Centauri system and perform precise course corrections throughout its approach. One possible method for landing on Proxima B is the use of a descent module, similar to those used during the Apollo missions to the Moon. This module would separate from the main spacecraft and use its own propulsion system to slow down and land on the planet's surface. It would need to withstand extreme heat and pressure during entry, as well as the potentially harsh conditions found on the surface. Another option is the use of a rover, allowing scientists to explore the planet in far greater detail. The rover would be delivered to the surface by a descent module and equipped with a wide range of scientific instruments, including cameras, spectrometers, and drilling tools. The rover itself would need to be built to endure the challenging environment of Proxima B, including possible high radiation levels. Regardless of the approach, the landing must be executed with extraordinary precision. This demands accurate trajectory calculations and a deep understanding of the gravitational dynamics and environmental conditions within the Alpha Centauri system. To achieve this level of accuracy, scientists rely on a combination of analytical calculations and detailed computer simulations. These tools help ensure that the spacecraft can land safely and exactly where intended. Once on the surface, the mission would shift towards scientific exploration, studying the planet in far greater detail. This exploration could include collecting rock and soil samples, analyzing the atmosphere, and searching for any signs of life. The information gathered would be critical in assessing the planet's habitability and determining whether future colonization or even terraforming might be possible. How much can we truly learn about the exoplanet orbiting Proxima Centauri? The James Webb Space Telescope will play a key role in answering this question. It can analyze whether Proxima B is capable of retaining an atmosphere as it moves around its star from Earth. Proxima B would pass through different phases similar to those of the Moon, and infrared observations from the telescope could detect changes in the combined brightness of the star and the planet, likely following a repeating pattern throughout the planet's 11-day orbit. An airless world experiences extreme temperature swings. On the Moon, the side facing the Sun can reach around 242 degrees Fahrenheit, while the dark side can drop to about minus 290 degrees Fahrenheit. In contrast, an atmosphere helps distribute heat more evenly, meaning the difference between day and night on Earth can be only a few degrees. Observations like these can reveal how thick an atmosphere might be, since a thin atmosphere like that of Mars cannot regulate temperature as effectively as a dense one like Earth's. Light reflected from the surface of Proxima B could pass through a possible atmosphere and carry valuable information about the gases present. However, Proxima Centauri is far brighter than its planet, making that faint reflected light extremely difficult to detect. To overcome this challenge, astronomer Ignace Snellen and researchers at the University of Leiden have developed a two-part observational system designed to be used with the Very Large Telescope. Their approach involves using an advanced instrument known as SPHERE, which stands for Spectropolarimetric High Contrast Exoplanet Research. This system corrects distortions caused by Earth's atmosphere, allowing telescopes to produce much clearer images. With this improvement, the contrast between the star and its planet can be reduced dramatically, making the planet easier to detect. Instead of the planet appearing 10 million times fainter than its star, it may appear closer to 1,000 times fainter. Another instrument, known as espresso, can then separate the faint light of Proxima B from the overwhelming brightness of Proxima Centauri by detecting subtle shifts in wavelength. This effect known as the Doppler shift, occurs when the wavelength of light changes depending on whether an object is moving toward or away from the observer. Espresso can detect these tiny differences, allowing astronomers to analyze the planet's molecular composition in remarkable detail. If molecules such as oxygen or water vapor are detected, it could point toward the possibility of life. The Very Large Telescope may also be able to detect small changes in brightness as Proxima B rotates. If the planet has oceans, they could reflect light like mirrors, creating a brief but noticeable glint. Achieving this level of observation would require further upgrades to instruments like Sphere and Espresso, including improved coronagraphs and optical links between systems. Scientists estimate that within the next 3 to 5 years, we may begin to uncover details about Proxima B's composition and surface features. If the planet proves unsuitable for exploration, a spacecraft could continue its mission, investigating other planets or objects within the Alpha Centauri system. And while traveling to Proxima Centauri remains incredibly difficult due to distance, energy demands, time dilation, and radiation exposure, there is another way to experience it. You can explore it yourself from behind the screen. Today, video games offer immersive ways to journey across the universe. Titles like Starpoint Gemini, Warlords allow players to visit the Proxima Centauri system and navigate through environments filled with asteroid fields, gas clouds, and distant space stations, taking on the role of a space captain exploring the unknown. One of the most exciting aspects of Starpoint Gemini Warlords is the ability to travel to and explore the Proxima Centauri star system. Within this system, players can visit multiple planets and moons, each offering its own distinct terrain and environment. Among these locations, Proxima B stands out as one of the most intriguing, positioned within the habitable zone of its star and potentially capable of supporting liquid water on its surface. In the game, players are able to land on Proxima B and explore a world portrayed as harsh and unforgiving, filled with steep mountains, deep canyons, and active volcanic regions. Beyond exploration, players can also engage in combat with other spacecraft, taking part in intense dogfights or using advanced weapon systems to defend themselves. The system also includes space stations and various points of interest that players can interact with, adding depth to the experience. While Starpoint Gemini Warlords is not a scientifically accurate representation of the real Proxima Centauri system, it provides an engaging way to experience space exploration and understand some of the challenges involved in navigating through space. Another game that allows you to reach Proxima Centauri almost instantly is No Man's Sky. This procedurally generated space exploration experience enables players to travel across a vast number of star systems, including Proxima Centauri. Players take on the role of an explorer, piloting their ship through environments such as asteroid fields, gas clouds, and orbital stations. One of the most compelling features of No Man's Sky is its depiction of the Proxima Centauri system as a vibrant and colorful region, filled with diverse planets and moons. Each location offers unique landscapes, environmental conditions, and even forms of life, creating a rich and immersive experience. Proxima B once again appears as a key destination, imagined here as a lush and dynamic world filled with varied ecosystems and living organisms. Players can land on its surface and explore an environment that contrasts sharply with the harsher interpretations seen elsewhere. In addition to exploration, players can also engage in space combat, interact with stations, and discover hidden locations throughout the system. One of the most distinctive elements of No Man's Sky is its procedural generation technology, which creates an almost limitless number of star systems, each with its own unique planets, creatures, and resources, ensuring that no two journeys are ever the same. This means that no two journeys to the Proxima Centauri system will ever be exactly the same, and players can continue exploring and discovering new details even after visiting it many times. Overall, No Man's Sky offers a deeply immersive way to experience the Proxima Centauri system and reflect on the possibility of life beyond our solar system. While it is not a scientifically accurate representation of the real system, it still provides an engaging introduction to the challenges and wonder of space exploration. A real journey to Alpha Centauri would stand as one of the greatest achievements in human history, yet it would demand an extraordinary level of resources, technological advancement, and global cooperation between nations and organizations. The journey itself would be long and demanding, potentially lasting decades or even centuries, and the crew would face immense challenges, including time dilation, radiation exposure, and the need to remain completely self-sufficient. Even so, the scientific discoveries and knowledge gained from such a mission could be invaluable, reshaping our understanding of the universe and our place within it. A successful mission would not only expand human knowledge, but also open the door to future exploration and possible colonization beyond our solar system. It could inspire future generations to continue pushing the limits of what is possible. Beyond science and technology, such a mission would carry profound cultural and social significance, requiring unprecedented collaboration across countries, cultures, and perspectives, all working toward a shared vision. These possibilities, combined with the promise of new discoveries, make a mission to Alpha Centauri one of the most compelling goals in the future of exploration. The journey would be long and difficult, but the rewards could be extraordinary. With the right combination of technology, knowledge, and determination, humanity may one day reach the stars. If this journey made you see the universe a little differently, follow the channel for more explorations like this, because the next discovery might change everything.